We are on, again, page 4 in our Unit 1 notes packet. And we're going to start today with some review of graphing. So for this first sort of top of page 4, this is stuff you guys have seen before, but not for a little while. I know that you plotted points in geometry and sort of graphed figures in geometry, and you looked at transformations, but I believe that was towards the beginning of your year in geometry, and then you focused most of the rest of your time on properties of figures and not so much on graphing things on a coordinate plane. So this is stuff that you've seen before, but not for a while. So we're going to start with a little review of graphing for today. So remember, anytime that we're looking at plotting a point, we're given a description of that point in an ordered pair. And ordered pairs are always of the format x, comma, y. Okay? Our x-axis is that horizontal axis. Our y-axis is the vertical axis. And what we're looking at with an ordered pair is a description of how far to move from the origin. So the x tells us how far left or right to move. The y value tells us how far up or down. Okay? So we'll start at the origin and move according to the directions we're given in our ordered pair. So for our first ordered pair, 3, 7. Remember, 3 is the x value. It's alphabetical if you ever get messed up. So 3 means from the origin, I'm going to move 3 spots forward on the x-axis, 3 spots to the right, and then up 7 units. 1, 2, 3, 4, 5, 6, 7. And there's my point A. For B, same idea. My x value is negative this time, so that tells me I'm going to move to the left. So left 4 units, and then my y value is 1, so up 1. Here's B. For C, negative 8 means I'll move to the left 8 spots. And then negative 6 means I'll move down 6 spots. 1, 2, 3, 4, 5, 6. There's point C. I would like you now to graph point D. D is 10, negative 2. So I'm going to move to the right 10 units on the x-axis and then down 2 units on the y. There's my point D. E and F both have zeros as part of my ordered pair. So that means I won't move at all in the direction where I have the 0. So for point E, 0, 7, 0 for the x means I'm not moving left or right at all. But I am moving up 7 spots for the y. So 5, 6, 7. There's E. And then for F, negative 5 for my x means I'll move back to negative 5 on the x-axis. And then 0 for the y means I don't move up or down at all. So we'll stay here on the x-axis. Questions for me on plotting points? Okay. The other thing that you've done before, but not for a while, is graph lines, particularly lines in slope-intercept form. Okay? We saw this a lot in middle school. So when we have slope-intercept form for a line, that's y equals mx plus b as our general form. M is the slope of our line, or the sort of steepness of our line. Slope is always described as rise over run. So as I look at the slopes in my lines, they're fractions here. That top number tells me how far up to move, how many spaces up to move, or where my slope is negative, how many spaces down to move. And then the bottom number is the run. That tells me how many points to move forward. So for slope, I could be rising up or down. If my slope is negative, we're going down, but I'm always running forward. And then the B part, that number at the end, is my y-intercept. When I'm graphing a line from slope-intercept form, we're going to start by plotting the y-intercept. So we're going to start by looking at that B value. I want to start with the y-intercept because that is a point on my graph, okay? The y-intercept is where my graph crosses the y-axis. So I'll go to my y-axis at -9. Here, and plot a point. That's my y-intercept. So if I'm graphing from slope-intercept form, we're going to start by plotting that y-intercept. And then our slope is a set of directions for getting more points on the line. So from the y-intercept, we're going to rise 1 and run 2. And there's a new point on my graph. And then I can keep repeating these directions to get more and more points. So rise 1, run 2, rise 1, run 2, up 1, forward 2, up 1, forward 2. I may want points to the left of my y-axis on my graph as well. To get points to the left of the y-axis, we can take the directions that we used to get all these points and reverse them. So we went up 1, forward 2. We'll go down 1, back 2 to get points on the left side. And now we learned that when we graph a line, we want to connect all those points because the equation of a line describes not only the y-intercept and the points we can find nicely from the slope, but also every point in between those points. I've got a whole bunch of points on this line. Every point in between the points that I've graphed is also a point on this line. So we represent those by connecting the points that we've graphed. And then the last thing that we know when we graph a line is that we want to put arrows on the end because lines continue forever. We'll look at one more example here. So this was line L. So now let's look at line M. Again, we'll start by plotting that y-intercept. This time it's at 6. So positive 6 on the y-axis. And now my slope is negative. So this is telling me I'm going to go down 2 and forward 3. So start at my y-intercept, go down 2, forward 3. 1, 2, 3. Down 2, forward 1, 2, 3. Down 2, forward 1, 2, 3. And if I want points to the left, I could get those by reversing those directions. So we went down 2 and forward 3. I can also go up 2 and back 1, 2, 3. Up 2 and back 1, 2, 3. And just like we did for our first line, we'll connect these points to represent that every point that satisfies this equation, so all the points in between here, are also on the line, and our line extends forever, so we'll include arrows on both ends. And there's line M. Questions for me so far? Okay. Now, in Algebra 1, for every function that we talk about, we're also going to talk about problems, word problems we're used to seeing, problems with some sort of context. We're going to talk about data that we've gotten, and we're going to look at what that data, what shape it holds, what that data looks like. Okay, visually, if I were to plot this out, what sort of shape do I see here? In some cases, we'll have data that follows a linear pattern. In some cases, we'll have data that might follow a different pattern. And one of the things that we'll do is we'll take a look at that data and say, hey, I think we can describe this using a function. Okay, that's called modeling. We sort of did that yesterday when we looked at describing the patterns that we saw for those different sets of pictures. Okay, some of you guys gave me descriptions in words. We add 2 every time, or we add an increasing number every time. Some of you guys gave me descriptions that were expression-like or equation-like. So what we're going to do as a part of each unit, this function modeling, is come up with an expression or an equation, a function, that gives me what we're going to call a concise description. Okay, so a really neat mathematical way to be able to describe the information that we're seeing. Now, when we're using a function or an equation to model real life information, there's some other considerations that we need to worry about. So in some cases, we actually won't want to connect the points for our line or for our graph, okay? And we'll talk about why we might not want to connect points, but in some cases we won't. In some cases, I won't want to put arrows at the end of my graph or at both ends of my graph, because that doesn't make sense for the context of my problem. Maybe this is as big as my information gets or as small as my information gets. So we'll talk about that as well. One of the first things we're going to talk about is back to the first thing that we looked at here, X and Y. If I'm talking about information that I collected and I want to represent it in a graph, I have to decide what's the X and what's the Y. Okay? That's the very first thing we need to do. So on the next page, flip over to page 5 for me. That's what we're going to talk about next. If I'm looking at a problem with a context, okay, if I've collected some information and I want to be able to graph it, I want to be able to create a function model for my data, I need to decide what's the X value and what's the Y value. If I'm going to graph it, something has to be X and something has to be Y. So we determine this by asking ourselves, what's the independent variable and what's the dependent variable? Those words might sound familiar from your science class. It's because we're asking the same question that you would ask in your science class. So if you're going to do an experiment, right? I think that ducks at this pond like crackers more than they like bread. Okay? What I need to do is determine what's the independent variable, the thing that I'm controlling, and what's the dependent variable, the results I'm going to get back. Okay? And we need to do the same thing in math. So the independent variable, the thing that I get to control, the thing that I'm in charge of or that I manipulate, we put on the x-axis. And the dependent variable, that sort of result that I get or response I get to the changes that I make, goes on the y-axis. So let's take a look at a few examples here. You want to figure out which brand of microwave popcorn pops the most kernels. You test different brands of popcorn to see which bag pops the most popcorn. What would be our independent variable here? The brand of popcorn. The thing that I'm picking are the brands of popcorn. So that's the independent variable. Brands of popcorn. What would be then our dependent variable? Exactly the amount of kernels popped. That's the thing I'm going to like count or look at once I've popped it. Number of kernels popped. Number 2, you're interested in how rising sea temperatures impact algae life. So you design an experiment that measures the number of algae in a sample of water taken from ocean sites with varying temperatures. What would be the independent variable here? Yeah, the thing that I'm controlling or that I'm selecting is the temperature of the water samples. So this might mean I'm in a boat and I drive around and stick a thermometer in the water and say the water here is 68 degrees, let's scoop a little up. And then I drive somewhere else and I say the water here is 75 degrees. Let's scoop a little up, I label it. And so I've got these water samples for all different temperatures. That's the thing that I am picking, are the temperatures of the samples I'm taking. Okay. And then how about the dependent variable? What am I going to look at once I've got my samples? Exactly right. How many algae are in those samples? I'm going to put the sample on the slide and look at it with my microscope. I want you to notice that there's a key word in here that can help me. Impact. I think that the temperature has an impact on the algae. I think this affects this. So this is something that I can change or manipulate. That makes it the independent variable. How about number 3? You're interested to see when you receive the greatest amount of notifications on your phone. Record how many notifications you receive every hour. Notifications would be the, so the thing that I am controlling is how often I sort of record the notifications. Do I get to pick when I'm sent notifications? No, this one's kind of tricky. Since I'm not in charge of, like, that would be cheating, right? If I said, like, Steven, you gotta like post something on Instagram or like my stuff so that I get notified, like that's cheating, right? I'm not in charge of when notifications come in, but I can control the like intervals of time that I sort of study. Does that make sense? Okay, so our independent variable would be time. Right? That's the thing I'm interested in, is the when. That's the question. So then our dependent variable would be, yeah, the notifications, how many I get. Number of notifications, good. And then our last one here, Metamora is conducting a study on home sale price value based on the home's square footage. Data on square footage and sale price is gathered from each real estate transaction in 2019. What would be the independent variable here? Well, I'm collecting it all from the same year. If I were curious if that value per square foot had changed over time, then year, square footage, right? My guess, my hypothesis is that the size of a house impacts its sale price. So our independent variable would be square footage. And our dependent variable, the price, the like home sale price. There's some more sort of key terms in here. If I look at this based on sort of flips it from what impact did. But I think that this is based on this. That means this guy would be the independent because it would impact this thing. Questions for me? Okay. So now remember, once I know independent, dependent, I know X and Y. So the independent is the X and the dependent is the Y. Turn to the next page for me. Because we skipped sort of the bottom of page 4, we are also going to skip the top of page 6. And I want you to hop down to connecting points. Depending on our data, we may or may not want to connect the points that we've plotted. To decide if we want to connect those points or not, we need to continue to look at our variables, but this time we're asking ourselves, are they what we call discrete or continuous variables? So discrete variables are variables where I would expect there to be gaps between my possible values. One example of that is shoe size. So you can have a shoe size of 6. You can have a shoe size of 7. You can have a shoe size of 7.5 or 8. Can you have a shoe size of 7.892? No, right? If you go to the store and look for this number on a shoebox, you are going to be very disappointed. That's not a shoe size. Can you have a shoe size of 6.25? No. You can have whole numbers. You can have halves. That's it. So if I were to plot something to do with shoe size, and I connected those points, that would mean that I could have shoe sizes in between 7 and 7.5. If I connect these, that's what I'm saying. That's why I wouldn't connect data based on shoe size. Does that make sense? That's a discrete variable. So we don't want to connect points for discrete variables. If you know somebody who has a baby, if you have like a older cousin or an older sibling, or maybe if you remember having younger siblings, pretty popular thing to do over the last few years is to take a picture of your baby every month for the first year of their life, a lot of times with a little like sign that says like their name and how old they are, and maybe like their favorite food, and then usually their weight and their length and number of teeth is usually on those as well. So if I'm filling out that board for my baby for number of teeth, I can put 2 or 4 or 5. I'm not going to put 6.5. Does that make sense? Like you've got 6 teeth, or the next one came in and you've got 7 teeth. You don't have 6.5. Okay, so that's where we see number of teeth is another example here as well. Now, continuous variables are values for which I could expect anything within maybe a given range. So one of the options on here is height. Height is a continuous variable. Can you be 5 feet tall? Sure. Can you be 5'8"? Yeah. Can you be 5'8.5"? Could you be 5'8.25"? If I change to measuring you instead of in feet and inches, if I measured you in maybe millimeters instead, could you be, trying to think of a reasonable height in millimeters. Could you be like 0.5 millimeters, like something and 0.5? If I've got a sensitive enough ruler or a sensitive enough measuring tool? Sure, right? Could I go down to like 3 or 4 decimal places if I have a really sensitive measuring tool? Could I measure your height like to a nanometer if I wanted to? Sure. Any value is okay. So that makes this a continuous variable. So if I'm looking at height, I may have heights of a few people based on some other factor, but we know that height can be any number. So it would be okay to connect these because I could have heights in between these values. Does that make sense for continuous? Okay. Now what I would like you to do is to come up with 2 more variables that would be discrete variables and 2 more variables that would be continuous variables. So I'd like you to think of 2 examples for each of these for me. What's one example? Closing size, did you have that for discrete or continuous? Discrete, very good. As I walked around, I thought I saw somebody else with clothing size. Yeah, clothing size is a great one. So if it's the small, medium, large option, there's no medium and a half, right? You got to pick one or the other. If it's a number size, brands tend to stick to either even or odd numbers. So you don't even get all the whole numbers. You get 2, 4, 6, 8, 10, or you get 3, 5, 7, 9. For guys, for your pant size, right? They do a number for that as well, but it's generally even numbers, right? 32, 34, 36, something like that. Distance traveled, discrete or continuous? Continuous, yeah. Distance is a continuous. Distance. What'd you say? Age, discrete or continuous? Continuous. Anybody ever ask a little kid their age? They tell you 4.5. Right? I'm 5 3/4. Right? Age we can count as a continuous variable. Weight, discrete or continuous? Continuous. If we think about a bathroom scale, those usually go to either the whole pound or maybe they give you 1 decimal if it's like a digital scale. I've got a kitchen scale that will give me 2 decimal places. If I worked in a fancy lab, I could probably have scales that give me 4 or 5 decimal places. So our precision is only limited by our tools, meaning we have a continuous variable there. Anybody have another discrete variable for me? Number of shirts? It's got to be a whole number, right? It's a shirt or it's not a shirt, right? Well, you can have 17 shirts or 18 shirts, but not 17 1/4. Yeah, people in a classroom. Stephen, I saw your hand up too. Number of notifications. Yeah, if we think back to our social media notifications example from earlier, that's going to be a whole number, right? I can't have half a notification. Any other comments or questions on discrete or continuous variables? I just had a lot of good examples. If I had any, you guys didn't. I had heart rate as a discrete variable. We're counting beats per minute, so that's going to have to be a whole number. For continuous variables, the only one I had that you guys didn't was speed. That's another one where our sort of precision is just limited by our tools. So when I think about speed, usually that's going to be recorded as a whole number, but that doesn't necessarily mean that it is a whole number. It just means that's what the when you drive through Germantown Hills, that's what the flashy radar guy can measure, right? He can give you a whole number, but it could be anything in between. Okay, so now let's put this all together. Okay, let's take a look at an actual example of some data that we want to graph. So on page 7, our scenario here is looking at how much water we use during a shower. So this says a typical shower uses 2.1 gallons per minute. So if I think about the shower head, I've got a little over 2 gallons that sprays out of that thing for a single minute. Okay, we're going to create a graph that represents our total water used during a shower. So for our time, we've got sort of time here, and we want to figure out how much water we've used. If I haven't turned the shower on yet, how much water have I used? None. So this is a 0. 0 minutes, 0 gallons used. I've turned the shower on and it's run for 1 minute. How much water have I used? Yeah, 2.1 gallons. Very good. What about if I leave it run for 2 minutes? Yeah, I need to add another 2.1 since I let it run for another minute. So this would be 4.2. For 3 minutes, I would use 6.3. For 4 minutes, 8.4. And 5 minutes. Very good. Okay, now, if I want to graph this data, the first thing I need to decide is what is the X value and what's the Y value. So I'm going to ask myself, what's the independent variable and what's the dependent variable? Yeah, time is the independent variable because that's the thing that I control. I decide when to turn the shower on and off. So if I'm controlling time, that makes it the independent variable. That means the dependent variable would be gallons used. Very good. Remember, independent is our X and dependent is our Y. So on the X-axis here, I'm going to label this as time. We're measuring time in minutes. And then the Y-axis, I'm going to label as gallons used. Since the unit of measure is part of the label, I don't need to worry about including it again. And then when I label numbers on my graph, I want to try to make sure I label them so that my data fits the graph well. If I label it so that a significant amount of my data is off of the graph, if I've got to like make points like way up and over here, that's not a good spread on my graph. On the opposite end of the spectrum, if I label my graph so that all of my data is clustered into like just a couple little boxes, that's also not a good use of my space on the graph. Okay, so I want to make sure I label it so that I can see it clearly. It's not off the graph, it's not all clumped together. For this particular problem, if we label, this will work for both of our axes, if we label it as each tick is a half, meaning 1 would be here, 2 would be here, we get a pretty good fit. So I'm going to label both the X and the Y axis this way. And then once I have my axes labeled, I can plot my information. So I've got the point 0, 0, 1, 2.1, 2, 4.2, 3, 6.3, 4, 8.4, and 5, 10.5. So I plotted my points. The next thing I need to decide is, do I want to connect these or not? Now we just talked about discrete and continuous variables. If I have any discrete variables, I should not connect my points. I should connect my points. Why? Time and gallons are both continuous variables, right? I can shut that shower off at any point. I don't have to wait for the next full minute. And depending on when I turn that shower off, that will give me my number of gallons, which again, doesn't have to be a multiple of 2.1. It could be any value. So I'm going to connect these because both variables are continuous. Continuous. There we go. So I'm going to connect these. And then my last question. Should I put arrows on the end of this or not? That's a solid argument. Could I take a shower longer than 5 minutes? I can, I have, and I frequently do. Okay, I would bet most of us have taken a shower longer than 5 minutes. I also saw a couple people shake their heads no. So if you said no, why did you say no? Could I take a shower less than 0 minutes? No. Like this would be talking about like 4 minutes before I turn the shower on. I don't care about that. So we're still not using any water if the shower's not on. So we can have an arrow on the right, but we don't want an arrow on the left. Now, it's worth noting, and one of my earlier classes pointed out, when we put an arrow on a line, it's because the line goes on forever. But when we talk about this context here, your shower won't realistically go on forever, right? You're not going to be in the shower for the rest of time. So there is some cap on here, okay? Some reasonable cap of how long it's okay to be in the shower. But we can be in the shower for more than 5 minutes. So 5 is not our cap. So we're going to put an arrow. Okay. For tonight, I would like you to try the problems on pages 9 and 10. It's the same idea as what we just worked on together. Pages 9 and 10, I want you to try for homework tonight, okay? Same idea, you've got a scenario. You're going to create a table to get some points. You're going to create a graph based on your data. And I want you to consider things like, what's the independent and dependent variable? Should I connect my points or not? And do I need arrows? So pages 9 and 10. What? I'll be right there, okay? Just hard to hear you over the air conditioning.